Yeah, I'll record this. Do you want me to quickly go over the previous problem? Or, all right. Okay, so yeah, all right. So if A has order 1, then A is the identity. Okay, so that's not going to give us an order 2 element by itself, but we do know that in a group of order 8 there are 7 non-identity elements, right? So every group, the group has 7 non-identity elements, right? So let's suppose A is actually not the identity, right? So then that leaves actually only 2, 4, and 8 are the actual possible orders. Is that okay? Then the order of A is 2 or 4 or 8. Okay? Now, those are just cases to consider. So case 1, if the order of A is 2, the problem says find an element, show that the group has to have an element of order 2. Well, if that happens, you're done, right? Then A has order 2. So you're done, right? The goal is to find an element of order 2. So you didn't get anywhere with the identity, but that's okay. We still have 7 other possible elements to consider. So these are the possibilities, right? So that's one possibility. Case 2, A has order 4. Now, what does that actually mean? You have to be very careful with the definition, right? The definition of being order 4 means that A to the 4th is E, and, right, the order has 2 components to it. That's the smallest exponent that you get the identity from, right? So you could either write that out as a sentence. A to the n is E, and n is this, you know. I don't want to write out that long sentence. So you know what else you could just say? You could just say A cubed is not E, A squared is not E, and A is not E. That's the same thing as saying the smallest such n where A to the n is E is 4. It's much faster to just say that. And it's probably more intuitive too, right? It's saying it's not the identity, the square is not the identity, the cube is not the identity, but that is the first instance that gets us to the identity, okay? So keep in mind that you can't just say that when you talk about the order. You also know these are these non-equations, and that is crucial to this problem actually, okay? Because we do know this, but can we build or find, how about I should say that, find an order 2 element? And the answer is yes, because if you stare at that equation, can you fill in the blanks? Can I find something whose square is E using this equation? Yeah, that is the same thing as A squared, right? We know A to the 4th is this, okay? And that's E. Now, this would be completely useless if we did not know that this, what do we know about A squared? We actually know that it is not the identity, right? So that is an element of the group, and its square is E, and A is not E. So check this out. So look at this. So A squared is in the group, and A is not E. Do we agree with that? Thus, we can conclude that the order of A squared is 2. See that? Because remember, you could just call it B. As long as you know that it's square. Do you guys kind of see this? Oh, okay, you know what? Let me expand on this. Okay, A squared is in the group. A is not E. A squared is not E. But now if I square it, which is A to the 4th, this is E. You guys see that? Maybe I should put parentheses here. So this is to the 1st power, right? So A squared to the 1st power is not E, but A squared squared is E. So the 1st power of A squared that got us to the identity was squaring it. See that? So that actually tells us that the order of this element is 2. Okay. You could, if you want to just, what's in red here, right? The red element to the first power is not the identity. That's okay. But if I square it, I do get the identity. So do we agree now that the red thing has order 2 by the same logic of what we're saying here, right?
So you use the same logic for
yeah. Now do the
order of
yeah. So see if you can do the same thing for that last case. So suppose that it had order 8 instead, then you guys do the same exact idea. Okay. All right. That's why you have to be very careful with the definition of order, right? Just knowing that if I, like, for example, if I told you this, but did not tell you the stuff on the right here, then it is possible that A had order 1, 2, or 4 actually, because it could be that A is the identity and this would be true. If A squared was the identity, then this would be true. Or if A to the 4th is the identity, then of course A to the 4th is the identity. But yeah, but keep in mind, yeah, this is a much stronger assumption. Saying what the order is gives you that equation and these non-equations. Okay.
That makes sense.
All right.
That's really what you would say for -5, because you would say that the order could be 1, 5, and 25.
Yes. Yeah.
You would say, well,
Yeah. That one has even fewer things to consider really, because showing the group is cyclic means that it's Lagrange again. Like everything is from Lagrange. Okay. So if the order is 25, then elements can only have order 1, 5, or 25, right? If the order is 1, then of course, then E to the 5th is the identity. If the order is 5, do you agree G to the 5th is the identity? And what happens if the order is 25? Then that would be, then it would generate the whole group, right? The cyclic subgroup that it would generate would be the whole.
I have one question. If G is E to the 5th, I mean, G is also E? Or...
Not necessarily. If I told you only G to the 5th was E, G could have order 5 or 1, which is what actually ends up happening, right? Yeah. If we have some more time, I can give you some more details on those. Does that sound okay? Let's see how much of the new stuff that we can finish. Did everyone get these notes? The new one? Okay, cool. Okay, so last time we did a few examples of isomorphisms, and then I sort of ended with, hey, it's sometimes is much easier to show two things are not isomorphic because all you got to do is just find something that one group has that the other one doesn't have, right? So for example, we could prove that Z4 is not isomorphic to Z8 because they have different orders. Or we could say S3 is not isomorphic to Z6 because S3 is non-abelian, but Z6 is. So here's the cliffhanger I left you on, which is U8 isomorphic to U10? Now, there's a back side to that sheet, so you could use the other side of that, but just so I can keep this here. Let's see, so U8, let's write out what the elements of each of these groups are. So U8, you got to write out what's relatively prime with 8. So 1 is, 2 is not, 3 is, 4 is not, 5 is, 6 is not, and 7 is. So it only has 4 elements in it. And this is going to be multiplication modulo 8. Okay. And U10 will have 1. It won't have any evens, right? 1 is then 3, 4, 5, 6, 7, 8, 9. Okay with that? And this one, multiplication modulo 10. Okay. Now, the next thing that you usually are going to do is, well, they have the same, first of all, they have the same order, right? Okay. I'm just kind of showing you a strategy. If the two groups are finite, this is kind of the strategy you use. Write out the elements, figure out first of all what the orders are. If they're the same, then that's not enough. You know, same. Keep going. And you're hoping that you find something essential that one group has that the other one doesn't. Is everyone okay with that? Just knowing that the orders are the same is not sufficient, as we saw in number 2 here, right? Number 2, S3 and Z6 have the same number of elements. They both have 6 things in them, but one is a non-abelian and one is abelian, so they're not isomorphic. Okay. So here they both have order 4, so maybe they are or maybe they are not isomorphic. We don't know just yet. Okay. So what's next? The next thing that you could do is you could start to look at the orders of the elements, or more generally, what are the cyclic subgroups that they generate? Okay. So for each element, look at the cyclic subgroups that they generate. The identity is always just going to give you the identity, so nothing fancy there. But let's look at 3. So 3, and then 3 squared is 9. 9 modulo 8 is 1. Right? Okay. 5. And then what's 5 squared? 25. Modulo 8 is 1, because 24 is a multiple of 8, right? Or you could just keep subtracting 8, right? And 7 is 40. 7 squared is 49, and 48 is a multiple of 8, so I know that modulo 8, that's going to be a 1 as well. Is everyone okay with this so far? Okay, so do you see that this already might be useful to us? Because over here, let's see what happens. So now let's look at what 3 generates. So 3 squared is 9, right? What's 3 cubed? 27. But modulo 10 is, so this is 27. But modulo 10, sorry, 10, this is 7, right? And then 3 to the 4th is 81, but modulo 10 is 1, right? Okay, so let me just write that a little bit nicer. 3, 9, 7, 1. Okay. So you can actually already stop right here. And you can give me several reasons why these groups are not isomorphic. Because look what you just did. Can someone give me a reason? Now, suppose you didn't say anything just now. Maybe you want to see what the rest of these things end up being. So 7 squared is 49. Modulo 10 is 9. And then 7 times that would be 63. Modulo 10 would be 3. And then 7 times that would be 21. Modulo 10 would be 1. 9 is a little nicer. 9 squared is 81. Modulo 10 is 1. Yeah. So this is a big fat no. And you can give me many reasons. Reason 1, you don't have to give me many reasons, but I'm just going to give you many reasons so that way we're all on the same page here. So reason 1, you said U10 is cyclic, right? U10 is generated by 3 or 7, you could say, right? Does everyone agree with that? But U8 is not cyclic because we didn't find any element over here that generated all the elements of the group, right? Okay. So that's perfectly good. And that's a pretty quick reason, right? So you just did a bunch of calculations and that gave you a conclusion about the group. So that's kind of nice. Reason 2, anyone see some reason? Yes. Okay. So which could you say? Sorry? Yeah, there's subgroups of different orders. So for example, U10 has a subgroup of order 4, and U8, well, U8 actually does, because U8 is its own, how about I say this, has How about this? Has only one subgroup of order 2. You see that?
Yeah.
Has only one subgroup. That's fine. Subgroup of order 2. And U8 has 3 subgroups of order 2.
I think I should use
Okay.
order 4 then, because you only has one subgroup.
What the reason I didn't want to say that was just because these actually are the whole group, right?
Oh,
So saying that they're subgroup, they still are subgroups, but it's not like you're getting a different subgroup of order 4 really, because they are actually the same. So how about this reason? Do you agree that these 3 elements have order 2, right?
Yeah.
So you could say U8 has 3 elements of order 2, and U10 only has 1 element, whoops, of order 2. Is that a pretty good reason? You see that only 9 has order 2, right? The element. And you could probably think of some others as well. But these are things to look for. So that's why the general strategy that I suggest is first figure out what the orders of the groups are. Okay, figure out what the orders of the groups are. Then look at the cyclic subgroups each element generates. And if they're still looking to be the same, maybe there's some more theory that we can evolve. Any questions with that? So definitely if you're trying to prove 2 groups are or are not isomorphic, this is a good strategy to attempt. All right. Okay, so now we can go on to the new note set. Okay. Now, one thing actually before we do, last time I was looking at the numberings. I was redoing this note set. It used to be shorter, and somehow I screwed up the numbering. So this note set was actually 13. Okay, the one that you just finished. I'm sure that left you all in suspense, right?
Yeah.
But just so that way you didn't think you were missing a note set, right? Because that probably would be a little stressful if you were going through your notes. You're like, what did I do with note set 13? Okay, so this one is note set 13.5. And the reason I had to do that is because I already think I've given you all the filled in notes. I just created this note set for you guys. Okay. Yeah, well, it would just make, yeah. So it's easy to just, give you a something in between. Okay. And I wanted to give you guys some nicer notes because a lot of this stuff that I have here is kind of just handwritten, at least in the filled in notes. Right? Didn't I give you a link for the filled in notes? Okay. So I think this will probably end up looking a lot nicer. Okay. Properties of isomorphism. Okay, so the first thing I just wanted to show you, kind of continuing off of the idea that we just talked about, is, well, we had a list from the previous note set that looked like this. Okay, so these are isomorphism properties in general. Okay, and now let's look at isomorphism properties specific to elements. Okay, that was kind of more involving the entire group, like global structure or subgroups, right? So this is more localized structure. Okay, so suppose that you have an isomorphism, and again, there should be a space here. So I guess I clearly copied and pasted that part, but forgot to add the space there. So an isomorphism of 2 groups. So the first property says, if you happen to have an isomorphism and you wanted to build such a thing, or say you wanted to build it from scratch, right? And you were trying to build one, you definitely always have to have the identity maps to the identity. So the identity of G will have to map to the identity of H. Okay. The proof of that is actually really short. Maybe I'll show you the proof for one here. So let EG be the identity of G. Okay. Do you agree, by definition, of the identity, I'd have to have EG times EG is equal to EG You guys agree with that? All right. It looks pretty useless, but I'm going to turn it into something useful. Okay, now I'm going to act phi of on both sides of this. Okay. Now, what can I do with the left side here? Anyone have an idea? I know that phi is an isomorphism. So if you look back at the properties of an isomorphism, okay, an isomorphism is a bijection. So it's a nice function, it's one-to-one and it's onto, but I have this last property that says anytime you encounter the a product, phi of this product, you can break that apart as phi of A times phi of B. Now, if this happens to be a sum, it's the same idea. Like you can break it apart based off of whatever the group operation is. Okay, so what I'm saying here is because phi, so since phi is an isomorphism, what can I write? I can actually say I can break this apart as phi of EG, phi of EG. Everyone okay with that? Like the left, we can simplify the left. I could have probably made this a lot cleaner if I actually flipped these, then you could just make one long string of equal signs, but whatever. But now we're actually done, because look at this. You have an element times the same element is equal to the same element. That looks weird. The only way, okay, let me cover this up and give you some more intuition. So let me cover this element right here up. Okay. Do we all agree that phi of EG is something in H? This is in H, right?
Yeah.
Okay. Now, if I take this element in H and I multiply by the mysterious element under this marker and I get back the same element, then by definition, what's under this marker has to be the identity. See that? So by definition, this must be the identity of H. Okay, so that is phi of EG, which is that element right here, is equal to EH. Okay, that's it. And really, I didn't even need the one-to-one and the onto property. The only thing I actually needed was that fourth property. So later on, you'll see that that'll be somewhat important. Okay, I didn't need the one-to-one or onto. I did need that it was a function because I needed to know that these things were in H. Okay. Seems kind of useless right now, but if someone claims to you that you have an isomorphism, but the identity gets mapped to a weird non-identity element, it can't possibly happen. Okay, it must be that the identity must map to the identity when you have an isomorphism. If it was just an arbitrary function, that doesn't have to happen. Okay, but isomorphisms are special. Next property, if n is an integer and you give me any element to the group and I take phi of a power, then it turns out that I can do phi of a and then take the exponential power. And the proof of that is actually just comes from socks and shoes, not socks and shoes. It's the full proof is by induction, but can I just give you some intuition? Okay, so the proof of 2. Let's just call this a sketch, okay? You technically need induction for the full proof, but I'm hopefully going to convince you without using that. So let A be in the group, okay? What would phi of A squared be? That's the same thing as phi of A times A. Does everyone agree with that? And phi is an isomorphism, right? So what can I do to this product? Yeah. So this is phi of A times phi of A, since phi is an isomorphism. And that right there is phi of a squared. So do you guys kind of see where I'm going with? That's pretty much your base case. Yeah.
A to the N.
Yeah. So in general, it's the same exact idea. But again, when I say dot, dot, dot here, this is a sketch. You would have to do induction to prove this, but phi of a to the n would be phi of a times a, dot, 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 a total of n times. You know, anytime you're doing a hand wavy argument where you put a dot, dot, dot there, most of the time there's an actual induction proof there, but you're just waving your hands around. You know. And again, that would be phi of a times phi of a, dot, 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 phi of a, which is what we wanted. But there's some intuition there, right? Without having to go through the full-blown induction proof, which I'm sure you would have stayed fully awake and interested the whole time I did that, right? Because I sure would have, right? Okay. Yeah. Well, induction is pretty much like, if you know it for 2, then you know it for n. You'll see that in pretty much every course, right? They usually will state some nice thing for 2 properties, for 2 things, and then you know it for n. All right. Okay. I'm not going to prove all of these. Maybe we'll come back to some of them. But next one, if you have 2 elements in your group and they happen to commute, so that means A times B is equal to B times A. I'm not saying the group is abelian. I'm just saying that you happen to have 2 elements in the group that commute with each other, which can happen. Then the isomorphism has to carry that forward. The isomorphism has to preserve everything. The only thing it does not preserve is what you name the elements and what the actual operation is. Okay. It has to preserve pretty much everything else, though. It's like a dictionary, right? So the image of these would have to commute as well. Similarly, if G is cyclic and A is an actual generator, this is actually stronger than what we said last time. So if G is cyclic and A is a generator, then H is not only cyclic, but it actually has to be generated by whatever the forward image of that A is. So the isomorphism actually has to preserve the generators. That fact right there could be quite useful for you if you ever had to build an isomorphism, because then it can kind of pigeonhole what you could send things to. You see? 5th property, we're going to have something even stronger than this anyway. You won't ever need that to actually build the isomorphism, but if you had to for some reason, you could use it. 5 is saying that orders are preserved. So whatever the order of A is, the isomorphism you build, you have to send it to an element that has the same order. That fact right there is actually quite useful for you. So for example, let's say you wanted to build an isomorphism between these 2 groups. It didn't exist, but let's say you did want to. I would have to send this guy, the number 3, to an element of order 2, which would mean I'd have to send it to, say, 9. And now I get to 5, it has order 2. Well, I have nowhere to send it because there's no other element of order 2. So that's how you could kind of use that. Last one, if G is finite, both G and H have exactly the same number of elements of every single order. Okay, same number of elements of every order. Just wanted to give you a list of some properties that had to do with elements. I encourage you to try to prove all those properties. They're not terrible. The proofs are super long. But now let's talk about, I guess, another punchline of the course. So now we're getting at an actual full classification. Now we had a fundamental theorem of cyclic groups, but right now what I'm actually going to do is classify cyclic groups, which means that once you tell me they're cyclic, I actually know exactly what type of group you're talking about. Right? So the classification is quite short, actually. Suppose G is cyclic. So you have to know that. Okay, you cannot. So suppose G is cyclic. If the order of G is finite, it is infinite, then it must be isomorphic to Z. That's pretty strong. Right? So every infinite, so in other words, all infinite cyclic groups are isomorphic to the integers. This is under addition. And if the thing is finite, then it's got to be isomorphic to Zn. Okay, and that's it. that is, all cyclic groups of order n are isomorphic to Zn. So this is a very strong, very, very strong statement. Pretty much as soon as you tell me that it's cyclic, I automatically get these isomorphisms for free. And well, you'll see in just a second how powerful that can actually be. Okay, you can prove other group types are isomorphic without even having to build the phi. Okay, you get them for free essentially. Okay, now the proof. How in the world do you prove that? Well, you have to build an isomorphism. All right, so I'm going to do it for the first one, and then okay, so let's prove. Let's call. Maybe I'll call that A and this B. So let's do the proof of A first. Okay, so the proof of A. Let phi go from G to Z be defined by what? Okay, so what we're going to do, so let me explain this a little bit. So where did A come from? So I probably could write it here, or I could write it after. Now, what are we assuming? We're assuming that the group is cyclic, right? So if the group is cyclic, it has a generator out there, and that's the A that I'm talking about here. Okay, so maybe I can write here. So let G be cyclic. So that means there exists a little A in the group such that G is equal to this. The cyclic subgroup that A generates is the whole group. Okay, and suppose the group has infinite order. Technically, when you write that, it's a little vague, but in all these cases, it's going to have to be countably infinite anyway. So if you want to be super technical, you can put LF not there. But if you have no idea what I'm talking about, just ignore the last 10 seconds. Okay, so is this okay now? Does this make some sense? What you're doing is you're taking your generator. Every element of the group can be represented as some power of A. So I'm just going to send it to whatever that exponential power is. That's how it's defined. So the first thing I guess you should check is, well, what's the point of this? So this is my phi, and let's show phi is an isomorphism. So if I show phi as an isomorphism, then I will have G as isomorphic to Z. So this is kind of the clever part here. So that has the first step, which is this well-defined? So is phi well-defined? Okay. In other words, is it a function, right? So if you ever hear this, so is phi a function? All right. Well, in order to prove that, I have to actually make sense of what are my inputs. Let G be an element of the group. Okay. Does everyone agree that since this group is cyclic, since A generates this group, there must be some K in the integers such that G is equal to A to the K. Does everyone agree with that? That's what it would mean for the group to be cyclic. Everything should be representable using this little A here. You okay with that? Like, remember, by definition, what is this cyclic subgroup that A generates? It's all the powers, right? All the powers such that n is an integer. And you could write it out in its list form. But do you agree that if I'm assuming that G is equal to this collection, then everything in G should be something of that form, right? So I'm just saying there is some K out there where this is true. Therefore, thus, if I map G, that's going to go to what I define. And this is K. And this is K an integer? Yes. So we're good, right? In other words, everything in the domain gets mapped to something in the codomain, right? So it's a well-defined function. Right? Domain. So this is in the domain. This is in the codomain. That's really what you're just checking. Everyone okay with that? Okay, what's next? Let's do something more interesting than checking that this thing is a function. Next. Yeah.
How did you know to define the isomorphism?
Yeah, that's a really good question. How do you build these things? They're really not trivial at all. So my short answer is, right now, most of these fees are going to just look like you're pulling them out of a hat. Okay, and as we learn a little bit more, you'll get some more intuition. Okay, so the next exam, I will not make you build any fees. Okay, so you don't have to panic about it until the end of the course, really. Yeah, for the next exam. So it's just up to isomorphisms. Yeah, it's, yeah. So up to whatever we do today. Now the thing is, yeah, I was going to ask you, we can do one of two things. We can either take the exam next Wednesday, or I could give you a, so if we do it next Wednesday, I'll post an assignment that you will not turn in on isomorphisms, this first stuff, but you should do the problems to practice. Or I could push the exam ahead 1 week. It would still cut it off to today, to whatever we do up to today. But then you would have to turn in a homework on isomorphisms next week, and then you'd have the exam the following Wednesday. So it's kind of up to you guys what you would prefer. Yeah, you can either do it next week or the week after. If you choose to do it 1 week later, then whatever the homework is.
We all do it on Wednesday, or, yeah, I would do it next. I'm okay with it.
Yeah, it would be a voting. I mean, is that what you're saying? Yeah, it's up to you guys.
You could be like, you can choose whatever one you want. Like,
Oh, no.
everyone is-
Everyone's, well, then I have to make 2 tests, right?
that seems like an accident.
Yeah. So if anyone has a preference on that.
Yeah, I'm okay with pushing it back.
Okay. Well, I mean, the advantage to that is you'll get more feedback on the isomorphism stuff before you're tested on it too. So that's good. Yeah.
But we still, like the content, like Kelsey's asking, will isomorphisms be on it?
So the types of questions you would expect is something like what we actually have already covered. So it would be something like, something like this, where I will give you the fee. You will not have to produce this,
Okay.
but then you will take this and you will do the 4 steps. So I absolutely will guarantee you'll have one question like that.
Sure.
Okay. Then,
It's gonna be like this next week or the week after.
yeah. And then the ones where you do not need to build the fee, they will either show that they're not isomorphic by exhibiting some property one has that the other one doesn't. So just like we did with that example, or like the example we're about to do, where you can use this classification. You don't have to memorize this proof. We're just proving it so that then we can use it, right? It's like I'm proving how a wrench works, which you don't care about, but then now that you have the wrench, then you can use it. Yeah. I'm proving to you that the wrench will actually work and not fail on you, but yeah. The advantage to doing it 1 week later would be that you get the feedback on the isomorphism stuff before you're tested on it. Yeah. Well, whatever is going to happen, I'm probably not going to do the homework. That would be you wouldn't turn in the homework that's due the week after that, because I'm still probably.
Either way, you're missing. Yeah, that's. I'd rather.
It's actually most students actually like the next homework assignment because it's a lot of these fee 4-step things. It's not actually. It's probably one of the easier homework questions.
Let's do that.
Okay. Is everyone online okay with that? That you'll take the exam in 2 weeks from today rather than next Wednesday. So if we move the exam, yes. Yeah. So we'll still cut it off to what we're kind of covering today. Okay. And what that means is next week, we're going to move on to some stuff that won't be on the exam. Yeah. And then the Monday before the exam, we'll do some review and maybe a little bit of new stuff. Okay. Okay, so second property, you got to show that it's one-to-one and onto, and that it's operation preserving. So first thing, show phi is one-to-one. So I also wanted you to see this because we're still following the procedure. So it's actually good to see for practice purposes. So now, to prove that it's one-to-one, you give me two things in the domain and show you suppose, yeah. So you could call them A or B or and whatnot, but the fastest thing would be to just use the form. So suppose A to the K and A to the J are in G, right? This would just save you one step, okay? Suppose these two are in the group. Suppose phi of A to the K is equal to phi of A to the J, okay? And what are you gonna show? You're gonna show they're actually equal to each other. Well, if that's true, then you have K is equal to J, because that's what phi does to those. Well, then certainly A to the K is equal to A to the J. All right. How about onto? Phi is onto. Suppose, let's say B is in the codomain. Okay. Can you find me something that maps to B? Yeah. That's probably the easiest onto proof, right? Consider A to the B, which is in the group, then phi of A to the B is equal to B. So you're done. Yeah. You got to find something in the domain that gets mapped to that, right? That's it. And then here's the new property, right? So the technical thing you're saying is phi is operation preserving. Okay, now give me two things in the group. So again, let's say A to the K and A to the J are in the group. And then you're going to show, if I do phi of their product, everything I've been working with G is their product, is equal to what? So it'd be phi to the AK and phi to the AJ. But in the codomain, what's the operation? Yeah, because it's in Z, right? Because this is in Z. Over here, this product is taking place in G. Okay. So what I usually do is just fill those in and then change whatever the operations are. And I kind of told you 95% of the time that's either plus or multiplication, and that's plus or multiplication, but you have to figure it out from context, what you're showing. And I highly, highly suggest you always write that step out, because you will get some partial credit, at least, for knowing the equation you're trying to get to. I feel like it's a lot easier to read now. Is it easier to read for you guys? I turned on this HD feature. I had no idea that it even had, but before it seemed kind of fuzzy, the image quality. Okay, so phi of A to the K times A to the J. Now, phi doesn't actually know what to do with that, right? Yeah. First, you got to write it so phi knows what to do with this thing, right? Yeah. A to the K plus J. And now phi knows what to do with that. What I mean by this is, look back up here. Phi knows what to do if you hand this is like a machine, right? If you hand it something of the form A to an integer, then it'll just give you the integer. But down here, it doesn't know what to do if you give it a product in that particular form.
And are you assuming like multiplication?
This actually, to go from here to here, is actually a notational thing. So there's no, it looks like you're doing a rule of exponents, but it's allowable. Yeah. I mean, it is a rule of exponents, but it's also a notational thing, because this means A times itself, K total A's, and there's J total A's. So together there's this many, right? And therefore this is K plus J by the definition. And that right there is phi of A to the K plus phi of A to the J. So you're done. So thus, phi is an isomorphism and G is isomorphic to Z. Okay. To prove B, think I can fit it right here? I'm just kidding. The only difference is you just add a mod n after the K, and that's it. Use phi goes from G to Zn by phi of A to the K is equal to K mod n. Okay, so the proof is it couldn't possibly be more identical than what you just wrote, because all you do is just write mod n after every single step up here. There's literally nothing that's going to be different. Okay. Okay. Now let's start to think about how useful this is. Well, you just classified cyclic groups. I kind of have to put that in a context of what that means, but if as soon as you tell me the group is cyclic, it's either Z or it's Zn, right? But it's isomorphic. It's not going to be this, it might not be the same object names and things like that, but knowing that it's an isomorphism, you're effectively saying they are the same group, right? I'll explain that in just a second. But that classification of cyclic groups actually gives you immediately the classification of groups with prime order. Okay, suppose G is a group of prime order. Okay, so where P is a prime, right? Then it turns out that the group actually has to be isomorphic to ZP. Okay? So that's kind of amazing. That's actually saying even if you give me a prime that's a huge prime number, it must the group, if it has that order, must be isomorphic to Z of that prime. Okay, and the proof is really short. What were you going to say? Sorry.
Isn't it just directly from B from the classification?
Well, okay. B has, okay, we got to be a little careful because B actually has two assumptions, right? Do you see that? If you just look here, it looks misleading, but remember, we actually assumed that the group was cyclic, right?
Oh, I
So
see.
suppose the group is cyclic and you know these things, right?
Yeah.
Then you get this. Okay, so if you could prove that if it's prime, then it's cyclic, then it's from B, and that's actually exactly what you need to do. Okay, so the proof is this: if the order of G is prime, then by, can you guess the name?
Lagrange?
Yeah, Lagrange. One of the parts of that theorem was that the group must be cyclic. By Lagrange, G is cyclic. Okay, and now by B up above, now by the above, since it's cyclic and the order is prime, I know that it's isomorphic to ZP. See? So that's why I should have actually labeled this. This is actually a corollary. Your teachers taught you the difference between these words, right? Like theorem, it's usually like a major result. No one ever talks about it. So theorem is like a major result. Proposition is like a little result. A corollary is something that follows almost immediately from a major theorem or some kind of result like that. A lemma is usually a little result, kind of like a proposition, but it's usually a little bigger usually. But it usually helps you prove the main theorem. So there you. Yeah, so lemmas and propositions usually help you prove bigger results, and then once you have that big result, you might get some smaller results after the fact, and those are corollaries. Yeah. Yeah. Mm-hmm.
Like, it was just kind of awesome.
It's not, there's no formal definition of what they really should be, but that is generally the consensus. You have these little lemmas that help you prove a main theorem, and then you have corollaries that follow. There's one book where the author writes all the major theorems as corollaries, and it kind of looks funny because there's no theorems. Everything's a corollary of the lemmas, but whatever. See, that's why it's personal preference, and it doesn't really matter. I'm just pointing these things out if you've ever questioned what in the world what we're doing. Okay, so the previous page hints at what are the main goals of this course in essence. Now that we have this definition of isomorphism, the main goal should be to classify all groups, right? But by saying that, it's a little too difficult to really say to classify all groups. Instead, what we're going to do is we consider two groups the same if they're isomorphic. I keep saying that, but why is that? Well, you have this nice little theorem that says the isomorphism of groups determines an equivalence relation on the class of all groups. So does that actually make sense? Well, if you give me, okay, what is an equivalence relation? So let's piece that back together.
Symmetric.
Mm-hmm. And reflexive, right?
When you say like classifying all groups,
Mm-hmm.
or I guess like classifying groups, you mean like
Classify means describe in every possible way
okay.
what the group should be doing or behaving like, right?
So far, we've learned of some classified groups.
Yeah.
Like
Yeah.
integers. Or
okay, so what I mean is we have this we have cyclic groups, which is like a collection of groups, right? And now we just classified cyclic groups into this possibility that they are either the integers or they're Zn.
right.
And prime groups of prime order, turns out they have to be ZP. So what I mean now is, suppose I give you this question: can you classify abelian groups? What do those have to look like? In the sense that you can build for me many different abelian groups that have different object names and types, but do they end up being maybe isomorphic to some fantastic group that has nice structure to it?
Okay. But would you say like the integers or like that, like Zn, is that a classified group, or like what would you call that?
Yeah.
Some like primitive.
Well, yeah, I guess the this previous theorem where it says they're isomorphic to Zn, I could have chosen another type of cyclic group to make it isomorphic to that, but we just know Zn and Z so well that these are kind of like our fundamental base groups
So
in a way.
it's not like those are like classified groups. It's just more like they're.
No, those ones are just well understood,
Okay.
So you could have stated an equivalent theorem in terms of, for example, the nth roots of unity. That's a cyclic group.
Okay.
And this theorem is actually saying that it must always be isomorphic to Zn. That's what this theorem is actually saying. So I could have stated the same theorem, but put the nth roots of unity here instead. But we're choosing to use Zn and Z as sort of our basic understanding of what these groups should be, because those ones are sort of the most well understood ones.
Okay.
So you might, yeah. Does that kind of make sense?
Yeah.
Yeah. So by classify, I mean, can you at least narrow down your understanding of what that object is to a sort of a nice list of describable features that we then know extremely well. Or just it's fully classified to the point where I know exactly what types of groups you're talking about. That's probably a better way to think about it. Okay. Let me try to take away some of the abstractness of this. So looking at this part, isomorphism of groups determines an equivalence relation on the class of all groups. I mean, if you read that, it sounds like your brain is frying a little bit, but do you agree with this? So if G is a group, let G be a group. Do you agree G is isomorphic to G? So that you just proved the reflexive property. Okay. Now let's prove the symmetric. If G is isomorphic to H, then do you agree H is isomorphic to G?
Yep.
So that's symmetric property.
Oh, there's
And if G is isomorphic to H and H is isomorphic to, I don't know, J,
G's
then G is isomorphic to J. So that's transitive. So if I write it like that, it's pretty believable, right? That's actually what we're saying right here. The isomorphism of groups, that's the relationship when we're, our set here is a set of groups, but that actually is not a set, it's actually a class. So that's why we had to use this fancy terminology of a class of groups. So you have this massive universe of groups, okay? Groups. And in this collection, we're trying to classify them in the sense that I want to understand what each of these pieces are. Okay, just like in a zoo, right, or in biology, you want to classify things based off of certain characteristic types. You know, it's very similar in groups. Okay, so for example, the cyclic groups, they are now fully classified. They are either Zn or they're Z. Now, there are many other things that are isomorphic to these guys, but cyclic groups live within abelian groups. Right? All cyclic groups are abelian. So within the abelian world, I have classified a portion of it, but I don't know, I have not classified everything else yet. Okay. And non-abelian and all this. You can actually make this picture even nicer by subdividing it by finite and infinite as well. But going back to this, does this kind of make sense a little bit? So because this is true, then you have an equivalence relation on groups, and we're abstracting the notion of groups being equal by saying they're isomorphic. Okay. So if you looked at the equivalence class of a group, it would contain all groups, yeah, isomorphic to G. So in particular, if you had like Zn, right, in here, you would have mu n, okay, and lots of other things.
It's like when you said like if you do like a tiger isn't like the same as a lion, like they're both animals. So they're like equal in that sense, like they're animals.
Well, what you'd be saying there is two specific tigers would be equal under the same species relation, but they are not actually equal animals because they're not exactly the same animal, right? Just like here, I have two groups that are equal because I consider them the same because they're isomorphic, but they are definitely different, right? The elements are different and the operation's different, but they behave and act exactly the same way. So I consider those the same. And it really comes down to because of this fact. Okay. I mean, that is literally what you do in every math class. You have a new object and you have a notion of isomorphism, and then you're just trying to figure out when things are equal under that relationship. So you're abstracting the idea of what it means for things to be equal. Okay. So the modified version of this, so version 2.0, you could think of this as like the beta test for the problem, for the goal, which is that. But a much better version is to classify all groups up to isomorphism. So you're trying to look for these collections of groups, but a bunch of them might be isomorphic to each other. Okay. All right. That's kind of the goal. Now, let's look at a couple more examples. I think that's a good way to end. We still have 10 minutes, right? 9 minutes. So let's figure out, are these isomorphic? Okay, so U5 is 1, 2, 3, 4. And U10, I think we already wrote that one, right? 1, 3, 4, 5, 6, 7, 8, 9. right? They both have 4 elements in them. Order 4, order 4. So we got to keep going to figure out whether or not they're isomorphic. Let's figure out the orders. The identity has order 1. 2 squared is 4. 2 cubed is 8, right? 2 cubed is 8, but modulo 5 is what? 3, right? And then 2 to the 4th is 16, modulo 5 is 1. Okay? So you can write 2, 4, 3, 1, which is the whole group, if you want to write that. And 3, you get 3. 3 squared is 9. 9 modulo 5 is 4. 3 times 4, which would be 3 cubed, is 12. Modulo 5 is 2. And then 3 times 2 is 6. Modulo 5 is 1. Okay, that 4. 4 squared is 16. Modulo 5 is 1, right? Because it's 16, right? 4 squared is 16. Is everyone okay with that? 4 squared is 16, which is congruent to 1 mod 5. So you really only end up with 4 and 1 here. U10, you already wrote out all the elements for that one. So if you want to write them out again, you can. But if I can find it. Oh, there it is. Okay, so this is this. And 3 got us everything. And 7 got us everything. And 9 got us 9 and 1. Okay. So far, just staring at it, it looks conceivable that these seem pretty similar groups, right? But what's the fastest way to get to whether or not they're isomorphic? The fastest way is notice that U10 is cyclic, and so is U5. You guys agree that these are both cyclic? They're both cyclic and they have order 4. So what are they isomorphic to? Yeah, so C4 in this case, right? So look, so this is cyclic and order 4. So U5 is isomorphic to Z4. And this guy is cyclic and order 4. So U10 is isomorphic to Z4. Okay, and look, yeah, that's the cool part about that classification. So this is why you want it, right? You don't even have to build the phi anymore. It's already built for you. We already have that wrench, so we don't have to go out and forge a brand new wrench every single time we need a wrench, right? How about the next one? Next one is same idea, U5, but U12 this time. Well, I already have all the information for U5 up here, so maybe just write out what U12 information is. U12, 1 is in there, 2 is not, 3 is not, 4 is not, 5 is, 6 is not, 7 is, 8 is not, 9 is not, 10 is not, 11 is. So again, order 4. Now, as soon as I prove that U12 is or is not cyclic, that probably will be enough, right? Because I already know this guy is cyclic. So let's see if this one is. So I get 1, 5. 5 squared is 25, but modulo 12 is 1. So far, 7 squared is 49, but modulo 12 is also 1, right? Because 48 is a multiple of 12. So it's 1 more than that. I think of it like that. Like what's the closest number less than this that's a multiple of this number? Yeah. Yeah. Well, you could also subtract 12, right? Subtract 12, subtract 12, subtract 12, subtract 12, you'll get 1. The way I do it the fastest is I think of what is the closest number that's less than this that's a multiple of the number. Because you're trying to, yeah. 11 squared is 121. 121 modulo 12 is 1. because 120 is a multiple of 12, right? Okay, and do you see you're done? This guy is not cyclic. Look, this guy's not cyclic. Not cyclic. Thus, U5 is not isomorphic to U12. Not bad at all, right? So do you think you could do problems like that on the exam? Right? So I will not make you build the phi on the exam. So anytime it involves a phi, you will be given the phi, right? And then you just follow the 4 steps. If you're not given phi, I'm asking you, are they isomorphic or not, like this? And you would do this kind of process. So either you would write out this laundry list of properties and say, oh, they're different. Well, one group has this property, the other one doesn't. So they're not isomorphic. But you can also get that they're isomorphic without building a phi because we have that classification theorem. Okay. So if you want, you could say by the classification theorem of cyclic groups. Okay. Does that kind of answer your question about classification? I think that it's kind of a hard thing to fully answer. It's just you're kind of trying to get to the point where you have a huge collection of groups and it's describable in terms of this one nice group,
I
right?
think what I was thinking too much of is like, are the groups that we have learned already, are those fully classified groups?
So yeah,
Do you know what I'm
no,
saying?
okay,
Like, that's why I
okay.
think I was like, well, how do you know when it's fully classified?
okay. So now that we just did this example, I think it might help you understand your question.
Yeah.
Look at the UN groups. We know how they're defined, right? But they're not classified in the sense that, do you see that some UN groups actually are cyclic and some of them are not?
Yeah.
So I have not fully classified their behavior because there's something that's different in this family of UN groups.
Sure.
So if you want to classify, if you want a classification of something, you usually want it in terms of something that you just understand really, really well. And the ZN groups, they're this nice cyclic group that.
Yes.
Yeah.
That,
Yeah.
No, it makes sense now.
Everybody loves
Yeah.
integers. I don't think integers.
Yeah. Yeah. All right. I think that's a good place to stop because we only have 1 minute left anyway. So I guess I will see you on Monday, right?
What?
Well, if it was graph
I was
theory.
like,
Oh, because the broccoli. All right. I will see you guys.
Unless it doesn't class tomorrow.